All right, welcome back. Last class we introduced two kinds of tests for determining the convergence of series, and we introduced the comparison test, and then followed that up with the limit comparison test. And you might have been left with the impression that, hey, the limit comparison test kind of takes care of the kinds of problems that previously we might use the comparison test for, and you might argue that why do you need both? We're going to take a little comparative look at the two tests, and what we want to do is look at an instance where you need one and not the other, basically. So just that we're all on the same page, I'm going to restate these tests, and I'm going to use that same numbering system I've been using all along. So the test number 4 was the comparison test, and it goes like this. If you have two series, the sum of AN and BN, we're going to look at the terms of those series, and we're going to say that the ANs are positive, but always less than the terms in BN, beyond some N. Then, if the series with the larger terms converges, then the series AN with the smaller terms, less than BN, those must also converge. And secondly, if the AN terms diverge, that series diverges, then the one BN that's bigger than it is also going to diverge. So we're borrowing the convergence or divergence onto the other series. Very similar to the comparison theorem for integrals that we've introduced a while back. So we've seen that. I want to compare that to the limit comparison test, okay, which we're again going to write out here just so we have it for reference. Limit comparison test. Again, I've got these two series now, the sum of n equals typically 1 to infinity, and I've got the same thing for some bn. And we saw last lecture that if the limit is n to infinity of the ratio of these terms, not with the summations in them, just whatever that term is, the nth term, if the ratio of those two terms is a constant, and it can't be 0, okay, it's got to be a non-zero number, okay, it can't be infinity, that's not a number. The conclusion is that basically AN and BN are behaving the same way. And so that means then AN in the summation and BN in the summation both converge or both diverge. They do the same thing. And I guess we've got the one final little series to remember. These are the P series that we mentioned last class. They come up a lot in these comparisons, and it's because it's a series that its convergence is really easy to determine. So if you have something like 1 over n to the p, like 1 over n squared, 1 over root n, 1 over n to the 3 over 2, whatever it is, we know immediately that this converges if p is bigger than 1, and diverges if p is less than or equal to 1. Okay, and just a reminder, that p-series result came straight from the integral test, and I think that was test number 3. All right, so there we go. We've got our setup here, and what I want to do is introduce an example, and we're going to build up some intuition, like usual, and then we're going to pit the two tests against one another to see which one will work. Okay, so I'm going to slide this up here, and so we've got it up there for reference. Let's try a little example now. All right, so here's the question. Does the summation of 1 plus cos squared n all over the root of n converge or diverge? The usual old question. All right, so the solution. The first thing we want to do is form some intuition. And we form our intuition based on recognizing things in there that we've seen before and we've dealt with before. Particularly, I'm looking at that cos squared n. And you might, again, remember that when we dealt with the comparison theorem for integrals. Often, we would look at cos squared n, and I'd note that is a very special term because it's bounded between 0 and 1. Cos of n itself is always bounded between -1 and 1. It just oscillates. So cos n, cos n, sorry, just pause there for a sec. Cos of n just goes like this. You might call that n. There's cos of n, 1 down to -1, and just keeps continuing on like that. If I square the function, it's just going to go like this. Something like here, here, here. This is cos squared n from 0 to 1. Something like that, anyway. All right, so we do have this result now of that particular function being bounded, and that allows us to look at the series and bound that. So first of all, since the cos squared n term is basically bounded between 0 and 1, in some sense, as I go off to infinity in n, that term is not growing or decaying to 0 or anything like that. It's bounded between two values and just oscillating back and forth and back and forth. So what I'm thinking is, if I'm looking at the kind of the intuition step, I'm going to argue that 1 plus cos squared n over the root of n is basically going to behave like, and I don't care the number up top, it could be 1 or 2, it doesn't matter to me, but it's kind of like a 1 over the root of n. Those are the important things as I let n go to infinity. And what that tells me, by looking at that term, of course that's the same thing as 1 over n to the half. And that's a p series with p equal to a half, less than 1. And so, again, up from my little p series rule here, that's series 1 over n to the p. If p is less than 1, I'm expecting divergence. All right, so expect divergence. Now that step of intuition is always needed in these limit comparison and comparison tests, because I've either got to formulate the thing to compare to in the limit comparison test, or I've got to form that inequality that's guided by whether or not I'm expecting to converge and get underneath a convergent function, or diverge and get above a divergent function. Anyway, so I'm expecting divergence in this case. So now we ask the big question: which is the right test? And this is the question that we are constantly addressing in the same way that with integration we're constantly asking, what's the best method here to solve this integral, by parts, substitution, whatever it might be. In the same way, we look at these tests and wonder, okay, given a particular series, what's going to be the best test to apply here? We're going to try the two of them that we've introduced here, the comparison and limit comparison. So over on this side, let's do the limit comparison. Now this came out as looking a little bit smoother and less cumbersome than the comparison test last lecture. You know, just look at the limit as n goes to infinity, all those niggly terms that we're constantly trying to compare and knock off and make less than something else or greater than something else. That can be a lot of effort mathematically, and sometimes it just doesn't work for us. So we were expecting maybe the limit comparison test to be an elegant replacement of the comparison test. All right, so let's see what it does in this case. So first of all, my summation of an is just the series that I'm given. So it's the summation 1 plus cos squared n over root n. The bn is the thing that I choose, and it's something that I expect to characterize the long-term behavior of my an. And I just argued up top in my intuition step that's basically like 1 over the root of n. So that's going to be my attempt at my bn. It's going to be, well, it's probably going to behave like a 1 over root n long term. Now the limit comparison test says take your an and your bn terms and take the limit as n goes to infinity of the ratio of those two terms, an over bn. Okay, that's the limit as n goes to infinity of 1 plus cos squared n over the root of n. And then I'm going to divide by the bn, and that's, of course, the same thing as multiplying by the reciprocal. So 1 over the root of n in reciprocal form is the root of n over 1. Of course, that's nice and convenient because those root n's are going to cancel. And it leads me to the limit as n goes to infinity of 1 plus cos squared n. Limit comparison test says if you can get that limit to equal any number c that isn't 0, then an and bn behave the same way. I already know that the bn here, I immediately know that that's going to diverge because n is equal, the p is equal to 1/2. Okay, it's a p series. So I look down at my limit and I'm hoping this equals some number. And I think, well, what does 1 plus cos squared n do? Well, that's this function. It's moving along like this in n. Okay, cos squared n just oscillates again between 0 and 1, and then you're adding 1 to it all. But there is no number that this is approaching as n goes to infinity. It oscillates constantly. So just like cos of n itself has no limit as n goes to infinity, well, neither does cos squared n or 1 plus cos squared n. So this thing simply has a limit that does not exist. It does not approach any L, get sufficiently close to any limit L as n goes to infinity. It just oscillates. So the limit does not exist, and what that means is that in this case, the limit comparison test simply doesn't work. All right. The power just went off in my house. Okay, cool. Well, I'm going to cut this off. That didn't work. So we're going to go back to the first approach, and that's the comparison test. That was the first one I introduced last lecture. That seemed a little bit less elegant, but nevertheless, maybe works. All right, so again, I have my intuition, I'm expecting divergence. So let me just write that. I expect divergence. So I'm going to take this an term, this 1 plus cos squared n over the root of n, and I want to bound that as larger than some other function, and that other function I want to diverge. So this would be something simple, and when I say something simple, I mean almost always it's going to be a p series. And I want it to diverge because then I want to be larger than a divergent function. So this is my setup, and now I just go to work. 1 plus cos squared n over the root of n is larger than. Now this is easy. Cos squared n just makes the numerator larger, so if I remove it, I just get something smaller, and I can just simply remove the cos squared n. That is definitely true, that statement. Okay. I mean, technically you could make equal to in some cases, but even that you don't have to worry about. And now I'm kind of done. The term over here on the right, 1 over the root of n, is the term in a p series with p equal to 1/2. And that series obviously diverges. Okay, we've talked about that up here in our intuition step. So we've got our divergent function, and we've got the an, which is larger than that. So we've got all the components for the comparison test to work. So I'm going to write up my answer here and say that since the summation of 1 over the root of n diverges because p is equal to 1/2 less than 1, and then of course I know you're referencing the p series rule there. All right, so I go to my statement then by the comparison test. You always have to cite the test that you use. Okay, so by the comparison test, our more complicated an is 1 plus cos squared n over the root of n, always larger than 1 over the root of n, we just showed. Also diverges. All right, and what that means is for this particular example here, okay, this 1 plus cos squared n over the root of n, we tried the two methods. We had a good gut feeling that this was going to diverge. We tried the two methods. Limit comparison turned out to give us a limit that does not exist. And if the limit does not exist, there's nothing we can do with that particular test. We need the limit to exist and equal some constant c that's not 0. So we tried it, didn't give us anything. Over here, comparisons are a little bit harder to make, but definitely it worked. And so we ended up being able to claim irrefutably that this particular series does in fact diverge. So we've seen an example now where even though the limit comparison test seemed to be a little bit more elegant, maybe took care of issues that came up with the comparison test, there is still a wheelhouse for the comparison test. There are particular series where that is the best and possibly only test that you can use to find a result of convergence or divergence. So we'll keep that in mind. We're not just going to throw out the comparison test in favor of the limit comparison test. We do need them both to be able to solve all of our convergence questions.